Hello and welcome to the chapter 6. Today we will talk about alcohols, ethers, aldehydes, ketones, carboxylic acid, and esters. So the remaining part of all the most common hydrocarbon that we didn't discuss so far. So let's first talk about the functional groups and the general formula of of each type. So we have the alcohol group, and it's characterized by the functional group OH, the hydroxy group, bonded to some hydrocarbon chain. And the difference between alcohol and ethers are just that this H is substituted by a certain hydrocarbon chain of some rest here. We have like CH, something alkane or alkene or whatever. And so you can see that the hydroxy group is at the end when it comes to alcohols, but for ether it's in the middle, and the H is then just replaced by another hydrocarbon chain. So that's the difference, and we will see how these products are formed later on. We will discuss it because it depends on whether we start from primary carbon, secondary carbon, and we will discuss that. Then we have the aldehydes, and they have this carbonyl group here, which is C double bond O, and it's at the end. When it's an end group, then it's called an aldehyde. But when this carbonyl group is in the middle between two different hydrocarbons, but when this carbonyl is in the middle, so is in between two different hydrocarbon chains, then it becomes a ketone. So that's the difference between aldehydes and ketones. Same as alcohols and ether. In the case of alcohol, we said that the hydroxy group is an end group, and when it's in the middle, then the H is, of course, replaced by a full hydrocarbon chain, then it becomes an ether. Same for aldehydes and ketones. We have this carbonyl functional group. Whether it's at the end of the chain or in the middle, defines the type, the class of which this hydrocarbon belongs to, such as aldehydes or a ketone. And next we have carboxylic acids and esters. We already discussed many times the carboxylic acids. So let's recap. We have also this carbonyl here, but the functional group is all this one. So C double bond OOH is what makes a carboxylic acid. And for example, this one here with one C only is a methanoic acid, because it has only one C, and so on. And when this functional group is in the middle, so this C double bond O, the other O, and the H is just replaced by another rest here. So we have rest number 1, rest number 2. Then it becomes an ester. So these are similar, these are similar, and these are similar. Just the placement of the functional group is what characterizes these classes. Now we know that we discussed already that a CO bond is very polar, because if you remember, the three most polar elements of the periodic table are Fon. You remember the Fon, which is the fluorine, oxygen, and nitrogen. And any of these elements, when it's bonded to a carbon, we have a very highly polar bond, or for example, if it's bonded to a hydrogen. And the delta En between C and O is 1, so it's strongly polar. So any hydrocarbon chain that has a CO bond or double bond, so like if it has an hydroxy group or a carbonyl, so any CO bond has a polar part, And we already discussed that a polar bond is normally hydrophilic because it can create, when we have these partial charges, like a very strong delta minus and very strong delta plus, then it can create hydrogen bridges with the water, because you know that the water is also polar, made of polar bonds. And when this H, for example, has a delta plus here, it can create a bridge with the O, which has a delta minus. And due to this polarity, it's able to be dissolved in water due to these bridges, because they can stick together. So all these classes that we discussed, all of them have this CO bond. Of course, they have OH, which is also polar, but in particular, they have a CO. So for example, here, there is no OH, but there is a CO. So all of them have in common this CO bond, which is polar. So part of this element can be dissolved in water because it can create hydrogen bridges with water. And also here, because this one is delta plus, for example, this one is delta minus, they can, create these hydrogen bridges. And this is how they are dissolved in water. So this one is an alcohol. We already discussed it previously. This one has an end carbonyl group, so it's an aldehyde. And this one has a carboxylic group, so it's a carboxylic acid. And all of them have this CO bond, which is polar. And this is one characteristic of these classes. Yeah, of course, this one is nonpolar, and normally the hydrocarbon chain is some oily material which is not dissolved in water, so it's hydrophobic, and normally it's dissolved in oily material, like another hydrophobic material. And the polar part is, can react with water, and that's why it's hydrophilic. So it has part which is hydrophilic and part which is hydrophobic normally, depending on how long is the polymer, for example. But we will come to this later once again. We discussed that previously for those of you who attended the classes. So let's talk about the characteristics of alcohol. As we said, they contain a hydroxy group, and we call it, you remember the alkane, which is methane, for example, ethane, propane, pentane, butane, so on. Now the suffix will be "ol" to represent that it's an alcohol. So the alk is the general name and the hol is the suffix, and the alk is normally replaced depending on how many carbons we have in the chain. So if it's, for example, 1 carbon, then it's a methanol. If it's 2 carbons, then it's an ethanol, and so on. And these OH groups, so hydroxy groups, can be at the end. So an end, normally they have to be at the end, but they can be bonded to the end carbon or to a certain carbon in the middle. So for example, we have this carbon can be bonded with an OH, or this carbon can be bonded with an OH. In both cases, the OH is just an end group, so it's not bonded to from the other side to anything. It's free, so it's an end group, but it can be bonded to either the end carbon or some in the middle. And this is what differs or characterizes the name of a primary, secondary, and tertiary alcohol. Just like we have primary, secondary, tertiary carbon, the same way, depending on where this functional group, hydroxy group, is located, characterizes the primary, secondary, or tertiary alcohol. So if it's located at a primary carbon like this one, which is only bonded to one carbon, so it's a primary carbon, then it's a primary alcohol. If it's bonded to a secondary carbon like this one, then it's a secondary alcohol. And the rule of Erlenmeyer is that we can only have one hydroxy group at each carbon atom. So we can have, for example, a diol, like alcohol with two hydroxy groups or more, but every carbon will only have one OH. So we cannot, for example, have, instead of C here with two H's, that this H is also substituted with another OH. It's not possible. Only one hydroxy group should be located at each carbon atom. So a maximum of one hydroxy group at each carbon atom in order to be an alcohol, classified as an alcohol. And it can be monovalent, divalent, and polyvalent. So here we will see some examples. This one is called a methanol, as I said, because it's only one carbon. And when we have two carbons, 1, 2, then it becomes an ethanol. And you know that it's an ol, so it's an alcohol because it has this hydroxy group at the end as a functional group. Here we also have this functional group, so it's an alcohol. And how many carbons we have? 1, 2, 3, 4. So yeah, when it's not explicitly written, then it's a carbon. Sorry, this is only 3. Yeah, this is here, for example. So we also have a hydroxy group, so it's an alcohol, and we have 1, 2, 3 carbons in the end chain at the end, and therefore this is a propanol. In this case, we have 1, 2, 3, 4 carbons, therefore it's a butanol with a functional group. And all of them are primary alcohol because all these hydroxy groups are bonded to the primary carbon, which is the end carbon. You see, it's a primary carbon is one that is only bonded to one carbon atom. So this one is bonded to one carbon atom. This one is only bonded to one carbon atom. This is, for example, a secondary carbon because it's bonded to two carbon atoms. This one is a primary carbon as well because it's bonded to only one carbon atom. So therefore, since it's the carbon that has the hydroxy group, then this is a primary alcohol. Now, these are examples of secondary alcohols because the hydroxy group is located at a secondary carbon. Here is a secondary carbon as well. And how do we name those? So this is also a propanol because we have 1, 2, 3 carbon. And it's an alcohol because it has the functional group OH. But we have to specify 2 in order to mention that the hydroxy group is located at the second carbon atom. Otherwise, it's considered that it's just that this one has the OH, which is not the case here. So we have to write 2 because number 2, carbon number 2, is the one that has the hydroxy group. Here is the same. So we could, for example, name it 1, 2, 3, 4. But in this case, it will become 3-butanol. And by the rules and the nomenclature rules, we always tend to have the lowest number, the minimum numbers possible. And therefore, we start naming from, the end chain, which is closer to the branch. So the branched element here is the hydroxy group, and this one is the closer to it. So we start naming from here 1, 2, 3, 4, and therefore it will be called a 2-butanol because it has 4 different carbons. And 2 means that the hydroxy group is located at the second carbon atom, this one. And these are secondary alcohols because they are bonded to the secondary carbon. These are examples of tertiary alcohol because this is a tertiary carbon here. It is bonded to 1, 2, 3 carbon atoms. Therefore, it's a tertiary carbon. And it has the hydroxy group. So this is a tertiary alcohol because the hydroxy group is bonded to a tertiary carbon. And it's called, of course, we start counting. The longest chain is the one that to be considered. This is the longest chain. And therefore it will be named 1, 2, 3 or 1, 2, 3, doesn't make a difference. So the hydroxy group is located at the second carbon atom, and therefore it's a 2. Of course, we have a branch here, which is a methyl group, because it only has 1 carbon, so it's a 2 methyl 2 propanol. 2 propanol because the hydroxy group is located at the second carbon, and 2 methyl because the methyl group is also located at the second carbon. So it will be named like that. And here we have an aromatic compound. We already discussed the aromatic compounds, which are some cyclohydrocarbon chains with those conjugated double bonds, so which is varying 1 double bond, 1 single bond, 1 double bond, 1 single bond, and with a formula for n plus 2. So, for example, if we count the electrons that form the double bond, so only which are in the pi system. So for example, here we have 1, 2, 3, 4, 5, 6 electrons of the double bonds, and if we have n equal 1, n can be any full number. So if n equal 1, then we will have 4 plus 2, 6. So 6 belongs to this formula, and therefore this is also an aromatic compound. Here in this case we have this aromatic alcohol because it has the hydroxy group, and normally it's a benzene ring, so we can either call it hydroxybenzene because it's a benzene which has a hydroxy group, or the common name is phenol. So it's an alcohol and we call it phenol. So when it's a ring that has 1, 2, 3, 4, 5, 6 carbons with an alcohol, so if it's a benzene ring of 6 carbons, normally is the benzene, and has a hydroxy group, then it's a phenol. Here in this case, like we discussed, that each carbon can have a maximum of 1 hydroxy group. We have 3 carbons, each of them has 1 hydroxy group, and therefore it's a trivalent alcohol. So the name is propan-triol. Normally it should be propanol if it's only like 1 hydroxy group at the end, for example, but if it has 3 hydroxy groups, then it becomes propan-triol, and it's a trivalent alcohol. This one is called, normally it's an ethanol because it has 2 carbons, but it also has 2 hydroxy groups, and therefore it's bivalent, and it's an ethanediol. So it's bivalent because it has 2 hydroxy groups. This one is an ethene because it has the double bond and it's made of 2 carbons, and it has the hydroxy group, and therefore it's an ethanol, but the common name is vinyl alcohol, and it's commonly used in the textile industry as well, as a solvent to create some synthetic textiles. So normally if we do wet spinning our electrospinning, and we want to prepare the solution, and we want something to dissolve the other material. We use polymer, which is the polyvinyl alcohol, and this is the vinyl alcohol, so it's only the ethanol, but the common name is the vinyl alcohol, and it's polyvalent here in this case when it becomes a polymer. So it's the same ethanol but multiple times, so that this double bond will be broken and the same one will be repeated again and again and again. So we will have this vinyl alcohol many times, one next to each other, and we will learn about polymers in the coming chapters. So in this case it's polyvalent because this very long chain of polymers has repeated alcohols at repeated places, and so since it's poly alcohol, then it's polyvalent. And these primary and secondary alcohols can create different compounds. So for example, can lead to either an aldehyde or a ketone, and then from this we can get carboxylic acid, but that all is going to be discussed in the next chapter. So let's continue with the carboxylic acid. As we said, they contain the carboxylic group, and normally the suffix which is added is acid, and we also add the oic. So for example, methanoic, ethanoic, propanoic, and so on, and they are all weak acids. So we know that, for example, HCl, the hydrochloric acid, is a very strong acid, and if we compare the carboxylic acid, which are organic compounds with carbon elements inside, they are weak acids, and so their nomenclature, as we said, is similar to the alkanes and alkenes, and it depends on how many carbons we have in the main chain. And always the carboxylic group, of course, this carbon is part of the functional group, and it's always counted as number 1 in the nomenclature. So why is it considered an acid? You know, an acid has the potential to release an H+ ion, and for this it should survive for a certain long time as an anion. Otherwise, if it just gets its H+ back, then it's not really an acid, because it has to survive alone by itself. Therefore, this COOH group, this OH, you know, it's a polar bond, so delta minus, delta plus, and when this polarity grows further, then the electron of the hydrogen is closer to the O until it's completely released alone without its electron, so it's released as an H+ ion, as a proton alone. And the remaining molecule with this excess electron coming from the H will become a negative charge, and therefore it's an anion. And this anion should be stable and should survive by itself for a certain period for the acid to be effective and to be reacting as a real acid. Because then it can bond to another cation, for example, if it's surviving as an anion by itself, and therefore the H will be replaced by another cation coming from another molecule, and a certain reaction can take place. So how does this ion, or does this carboxylic acid like stabilize itself when it's in this anion form? It's because of the double bond between in the carbonyl group. And this is caused by an effect called a resonance. The resonance is when the pi system is delocalized, so it's not only with this O here between this C and CO, but it's extending over the whole system, the whole functional group COO. Sometimes it's here, sometimes it's there, and whenever it's here, then the negative charge is on the other O, because it is the one that released its H and preserved its electron. So now it has a third lone pair and it has a negative charge. But once this lone pair, the third one, is transferring to become a full bond with the carbon, so it becomes like for a certain time a double bond, then this second bond here of the second carbon is released and becomes a third lone pair, and therefore this O is the one that's getting one electron in excess and getting the negative charge. So it's always fluctuating back and forth. Sometimes it's here, sometimes it's there. And this lone pair is also sometimes becoming, because the electron system is delocalized, sometimes it's making a bond with the C, and sometimes it's just a lone pair over the oxygen. And this is how this negative charge, it's kept stable, because it's not always on this O, like localized in one place. Otherwise, the O will have a tendency with this excessive electron to bond with something else, to react with a certain cation. But if it's only there for a fraction of a second and then giving it back to the carbon, and then this one is getting the negative charge again, and so on, then it will survive longer without any cation. So it will survive longer as an anion with this negative charge. And this is why the carboxylic acid, so this functional group COOH, is an acid, because it can survive by itself without the H+. So an element that can release an H+ ion and survive without it is called an acid. This is a definition of an acid. And this is the case due to this double bond, which is delocalized, and this is the resonance effect that makes this anion survive. Yeah. Now let's talk briefly about the names. So this is a methanoic acid because it's only one carbon, and of course the functional group is COOH. So this is why it's a carboxylic acid. And we said we add oic acid, and methane, it's because it has one carbon. But the common name, the conventional name, is formic. And yeah, so everything that has one carbon is normally formic acid. And then when we have two carbons, we always don't forget to count the carbon that belongs to the functional group, because it also makes part of the full chain. So the carbon, which is part of the functional group COOH, and the other carbon form a total of 2, and therefore it's an ethanoic acid, and the conventional name is acetic. We have on Moodle a PDF file about these conventional names, so about the acetic name and the formic and so on. You can, for more information, review it if you would like to know more about it. So when you see this acetic, just know that it's ethanoic. Everything that is acetic, then it's 2 carbons. and so on. So here we have 1, 2, 3 carbons, therefore it's a propanoic acid because it has this functional group at the end of the carboxylic acids. And this one is 1, 2, 3, 4 carbons, and therefore it's butanoic acid. Let's practice some more. So you know how to count already. We have 1, 2, 3, 4, 5, 6. This is the longest chain. And then we also check the branched elements. So we have this one here, an ethyl group, because it's made of 1, 2 carbons. And this one here is just made of 1 carbon, so it's a methyl. This one is a methyl. And this one is an ethyl. And the rest is 6 carbons, therefore it's hex. And it has this functional group, so it's a carboxylic acid, so it's hexanoic acid. Yeah? So now let's check the branches. We can say that, oh yeah, we already agreed that the functional group always takes the position number 1, and therefore this is the carbon number 1. So let's erase this to make it clear. This is the carbon number 1. And then this is number 2. So we have 2 ethyl, 3, 4, 5 methyl, hexanoic acid, which is the rest. It's as simple. So why do we say 2 ethyl, 5 methyl and not 5 methyl, 2 ethyl? Because letter E comes before letter M in alphabetic order. So it's not because 2 comes before 5. Even if it was 5 ethyl, 2 methyl, we will still put the ethyl before the methyl because we organize them in alphabetic order. Let's do this one. It's also an hexanoic acid. 1, 2, 3, 4, 5, 6, let's say. This is the branched one, which is a methyl. And this branch here is not a normal ethyl because it has a double bond, and therefore it's like an ethene. Yeah, because an ethene is made of 2 carbons and a double bond. And therefore it's called an ethenyl when it's a branch. It's no longer ethene, it's not hydrocarbon chain by itself, it's a branch, so it's an ethenyl. And then this is number 1, carbon number 1, because it has the functional group. This one is number 2, so it's 2 ethenyl. 3, 4, 5 methyl hexanoic acid. This is the name. This one is the benzene ring that we discussed earlier. And it has this functional group of an carboxylic acid, therefore it becomes benzoic acid. This is the conventional name. This one is a special one. If you divide it in 2, we have 1 methanoic acid and 1 methanoic acid, all bonded together and forming like a mirror, and it's called oxalic acid. So ox is because it has this oxygen. And yeah, this is the conventional name. It's an oxalic acid. It's formed of 2 methanoic acid, one next to each other. This table is just to check the strength of the carboxylic acid, and you can see that all of them are just weak acids, as you can see. And you know this formula is specially to calculate the pH of weak acids. It's half pKa minus log C, which is the concentration of the acid. And we know that the smaller the pH, so the smaller the pKa, then the stronger the acid is. So we can see here from this table that the formic acid is the strongest among them. And the more we have carbons in the chain, the weaker the acid gets. So, for example, the acetic acid is considered a weak acid, and the others as well. It gets weaker and weaker.